Hello people, today I'm going to be speaking about complex numbers again. And De Moivre's theorem. I apologize if I didn't spell that correctly. Now, what we have to remember is from the previous video I made, if you haven't seen it, please go check it out. I speak about complex numbers in it. This is the basic notation for complex numbers, so we have a real part and an imaginary part. Now I'm going to describe this same statement in polar coordinates. So our A is going to be equal to r times cosine of theta. You may ask, where do I get this from? Well, I'm going to draw an xy plane with my real part and my imaginary parts. So, if I have a vector r and an angle theta, this is my number A, this is my number B. Now, essentially what I'm doing, I'm getting a triangle where our vector r is the hypotenuse. This is A and this is B. I hope you see how that translates. So this is A, this is B. This is theta. Now, sine of theta equals the opposite, B, over the hypotenuse, R. And with simple algebra, we find that R times sine of theta equals B. B equals R times sine of theta, and you can derive A similarly. Tangent of theta, we'll need that as well when calculating the angle. So what is the tangent of theta? Well, I guess you all know. The opposite divided by the one next to. Now, what else do we need to know? We need to know the length of our vector r. R is basically this. It's the length of our complex number, our real part, and our imaginary part. A squared plus b squared. That is how we calculate our length. And now I'm going to be speaking about De Moivre's theorem. Essentially what it states is that our complex number can be expressed in this form: cosine of theta plus r times cosine of theta plus sine I times sine of theta. Essentially what we're saying is we're stating this basically. There is no difference. This is equivalent to this. There's no difference. Now what we're going to do, we're going to go through some examples so you guys understand what is going on. So 1 plus the square root of 3 times I equals, first of all, we need to find out the length of our vector. R equals the square root of 1 squared plus the square root of 3 squared, which equals 1 plus square root of 3 to the power of 2 is 3, which is the square root of 4. The square root of 4 is fantastically 2. Now we're going to find out our angle. So the tangent of theta is the square root of 3, so b over a, and 1. So theta equals the arc tangent of square root of 3. Now what does the arc tangent mean? So what we're doing, you could picture tangent as x, and you could have x times theta, and what you're doing is you're doing an algebraic manipulation. So theta equals 1 over x times square root of 3. An arctangent can be described as, let's say roughly, equal 1 over tangent of theta. Again, arctangent is basically the opposite of tangent. It's an inverse function. It's not really fair to say it looks like this. This is not really the form. This is just a simplification so that you understand it. This is not true either. We're doing an inverse function, and I will publish a video on inverse functions shortly. But this is just a simplification so that you understand it. So that is the arctangent of theta. Now we know we could derive cosine of square root of 3 over sine of the square root of 3. What this is equal to. So our theta is 60 degrees, which equals pi over 3. This is very important now. So we are going to describe a complex number in De Moivre's theorem. So our R is 2 times, in brackets, curly brackets, the cosine of pi over 3 plus the sine of pi over 3. Okay, so we have to multiply both of them. Sine of 60 degrees is 3 squared over 2. Cosine of pi over 3 is 1/2. So essentially our z is, just let me scroll down, my apologies, z is equal to 2 times 1/2, which is 1, plus 2 times 3 squared over 2, which is 1 plus 3 squared times I forgot my I here. So, did we get the exact same statement as at the start? The answer is yes. Now, I'm going to show you a tricky example. A different one. So, 16i. How are we going to describe it using De Moivre's theorem? I urge you to pause the video and try it out for yourself. You're going to learn more that way. But if you don't feel confident, then you can just go with me on this one. So, our r is going to be, again, square root of, we don't have a real part, 0 squared plus 16 squared equals square root of 16 squared, which is 16. Now, our tangent of theta. How are we going to calculate our angle? Is it even possible? Now, our b, this is our b. This is our a. Now, we cannot calculate our angle. It is impossible. 16 over 0 is undefined. It doesn't really mean anything. So we'll stop at that. We cannot define it. It's just the point on our imaginary line, this 16i. Okay, now on to the last example, which is going to be the number 6 plus 0 times I. So again, this is our b, this is our a, our real part, our imaginary parts. Now, again, we calculate the length of our vector, 6 squared plus 0 squared equals square root of 6 squared, which is 6. The tangent of theta is equal to, b is 0, over 6. We can calculate this, it means 0. So theta is equal to 0 degrees. How are you going to describe this? Simply, very simply. So 6 times cosine of 0 degrees plus I times sine of 0 degrees, and I think you already know the answer. So this is 0, this is 1, so 6 times 1 plus 6 times I times 0, nothing. Z is equal to 6. Is that our start value? Yes, it is. Another thing I might mention, what De Moivre's theorem states is essentially this. If I draw a graph, the length of our vector is not changing. But our cosine values, these are our cosine values, these are our sine values, are constantly changing. So what's happening is we're sort of, by multiplying by n, which is n belongs to the whole numbers, we are changing our vectors. The vector stays the same length. We are sort of creating a circle. We are staying in that circle because our radius stays the same. Let's say it's 2. So what it states is that z is equal to, a plus ib to the nth power is equal to r times cosine of n theta, notice n, plus I times sine of n theta. That's another way to put it. If you play with complex numbers, you know that they have many relations with many other equations, like I'm sure you've seen Euler's equation, e to the I pi plus 1 is equal to 0. This is basically minus 1. That's why it's equal to 0. Anyways, I'm not going to describe this equation. I just wanted to show you some other places where you can find complex numbers. Another thing you might see, you might find Euler's formula, which is basically r times e to the I n theta, r to the nth power, or it can be written as so, a simple trick. These statements are equivalent. So